Okay, here we have another example. Uh, okay, so for this one, we need to calculate the phase currents, and this is so we are now gonna work with power. So for a start configuration, we have that the voltage in the phase, it's gonna be the line to line voltage over the square root 3. And in this case, the line to line, we always assume that they give us RMS line to line. So we have 400 over square root 3, and this is 231 volts. Okay. Now we need to find the impedance, and we know that the impedance in an inductor is equals to J omega L. So in this case, this will be J 100 times 10 to the minus 3 because it's millihenries. That's the frequency times 2 pi. And this is gonna give us J 3142 ohms. Okay. Now we need to find the current. So for, let's say the current, the phasor current in A. Now because we are in A, we have this line, this phase voltage with 0 degrees, and we divide by the impedance. We have 20 because that's the real part of the well, that's the resistance, so that's the real part. And we have our impedance of, this is ohms, so this is ohms. So here we're gonna have a current of 6.2 with an angle of minus 57.52 degrees. Okay. Now this is the phasor current for A. So if we want to write it in another way, we could write like 6.2 square root 2 cos of 100 pi t, because we have 50 hertz, 50 hertz is 2 pi. Okay, now here we have for phase A, we figure out that this is the angle. Now for B, it's gonna be the same magnitude. I'm just gonna, it's gonna take it. Okay, copy it here. Get a little faster. Okay, and we know that this phase is 120 degrees away from phase A. And if we do the same for phase C, you're gonna figure that this phase is 240 degrees from phase A. Now, this is in radians, so we probably should be writing these angles in radians, but I'm writing it like this so it is clear, the angles, because in radians sometimes it is not always clear, well, at least to me. Okay, now we have here the second point. Calculate power supplied by the source using the per phase analysis. So we have that the voltage in A times the current in A plus the voltage in B times the current in B plus the voltage in C times the current in C. This is gonna give us power. And we can also calculate it saying square root 3 of the voltage in a line times the current in line times the cosine of the angle. And like this we can just calculate the power easily doing all this math. So we have 400, that's what they gave us. 6.2 is what we got for the current, and we got the cos of the angle here, that's 52. And here we get that this is 2.3 kilowatts. So that's pretty simple. Now third part. they're asking us to uh, find the AB component of, or a alpha beta component of the voltage and current, and use it to calculate power. Okay, so we have done actually this before. Um, just so I don't have to do it every time, in MATLAB I put a simple script with generic variables to get like a simple expression, a generic expression. So here we know that this is our transform matrix for Clarke, and we have here the generic voltage. So it's just an amplitude. We have here omega t. This case is 100 pi, just leave it like this. Here we have minus 2 pi over 3. Here plus 2 pi over 3. So if you remember in one of the previous videos, we did this. Actually, we have it here with 300 instead of A. And I'm going to do the same for generic current. So we know that we have an amplitude and cosine of our omega minus an angle. And we have here the same. We have 2 pi minus 2 pi over 3 minus that angle. And we have plus 2 pi over 3 minus that angle. That is just the same that we have here. So that are our currents. So I just asked MATLAB to simplify the multiplication of the transform matrix with the generic, and that gives me the expressions for generic alpha beta components. So we know that it's going to be 3/2 the amplitude of cosine omega and 3/2 the amplitude of sine omega. So this one is alpha and this one is beta. So we can just write it here. Our first, we need to write our voltage equations. So we have 231, that's what we calculated. We multiply it by square root 2 to get the peak value. And we have omega t. This is our voltage in A. And our voltage in B is the same. And here we have plus 120. And now here we have our voltage in C. Let's just delete this ugly thing. So this is our voltage in B and voltage in C. And here instead of having 120, we are gonna have the 40. Okay. So our alpha component, we know that's gonna be 3/2. I'm just gonna write it so we have it always. Cosine of 100 pi t. And our beta component is gonna be 3/2 the amplitude and sine of 100 pi t. And similarly for the current phasors, in the alpha is going to be 3/2 the amplitude of cosine 100 pi t, but we're going to subtract an angle theta. And here again, we're going to have for beta, it's going to be 3/2 the amplitude sine 100 pi t minus an angle theta. Okay. So now we can just plug this and to calculate it. So we have 3/2 of the amplitude, and we know that the amplitude is 231 squared times square root 2 cosine of 100 pi t, and this is just approximately 488 cosine of 100 pi t. And for our beta component, it's going to be 3 halves times 231 times square root of 2 of, well, this is not sine, this is not cosine, this is sine of 100 pi t. And the magnitude is going to be the same, but we are going to have sine 100 pi t. Okay, so this is our alpha beta components for our voltage. Now we need our alpha and beta components for our current. So if we just plug the same as we did here, we are just going to get that this is 13.1 cos of 100 pi t minus an angle, that in this case is 57.52. This is degrees. And we have here beta, that's going to have the same magnitude, but instead of cosine, it's going to be sine. And we are going to have the same angle here. Okay. Now, in a previous video, we derived this equation to calculate the power based on our alpha and beta components. So at the end, we got that it was 2/3 of the multiplication of these two matrices. So this is the same as having 2/3 our alpha components multiply plus our beta components multiply. You can watch the, I think it's even in the same, yes, here we have how we calculated how we did the derivation. Okay. So we know that this is how we calculate power. So it's just as simple as plug in the values. So we have our alpha components and our beta components multiplied by 2/3. Just make it smaller here so it fits on the screen. Okay, so this is our alpha components plus our beta components multiplied. And again, if we factor out all the scalars or the constants, we get that this is 42.4261.9 times, this is gonna be cos of 100 pi t times cos of 100 pi t minus the angle that we calculated, and it's similarly gonna be sine 100 pi t multiply sine of 100 pi t minus the angle. Okay. Now if we do this, I just use MATLAB to solve this. To make yes, I just use MATLAB to simplify this. We got it is just the magnitude here times cosine of the angle. So 2 degrees. And now we can actually calculate this, and this is gonna give us 2.3 watts. So this is how we calculate power using the alpha beta components. Okay, so now it is asking us to simulate it in Simulink. So let me see if maybe I already have it here. Changing, simplify, Clarke transform example. I think this is this one. So it's asking us to simulate the circuit in MATLAB or LTSPICE. So for MATLAB, I just downloaded a package that allowed me to use inductors and resistors. This package is called Simscape. Okay, so with sorry for the for how disorganized it is. Okay, I'm gonna try to go piece by piece so it makes a little more sense. So first we have our sources. So we have here A, and this is 325. 325 comes from 230 times square root 2. That's what we calculated. There's gonna be our sources. So here we have 355, and this one is B with a phase shift of 120 degrees, and this one is C and 240D. And for all we have 50 hertz frequency. Okay. Now here we have the load. Okay, sorry. The loads. That's just gonna be the resistor and inductor, and the inductor is 100 millihenries. And we connected in star configuration. Just be careful with the polarities. Make sure that all the negatives are facing them. And now we are measuring current. So here we have current through the load, and here we have current through the load too. And here, and this one is a little bit more hard to see, but this is also current through the load. So here we have uh, I, I, IA, IB, and IC. Okay. So to calculate power, we remember that we said that it was gonna be each voltage in the line current multiply. So here we have voltage and current multiply. Okay, we have the voltage and the current multiply. So this is VA times IA. This is BV times IB, and this is BC. This is BC times IC. Okay, BC times IC. So when we multiply these three and just sum that up, that's gonna give us power. So I'm gonna write it here. And sure enough, we have our 2.3 kilowatts of power. Now, we are gonna do the same for our alpha beta components. So we know that our alpha beta is just gonna be our transformation matrix that has our 1/2 and 1/2 and our square root 3. So we have A plus 1/2 B plus 1/2 C, and this is gonna give us our alpha, and then we're gonna have square root 3 times B minus C, and that's gonna give us our beta. Then I just make this subsystem and copy it here and change it for the same for alpha and beta components of the current. We need both to calculate current. And then once we have our components, we just need to multiply them by 2/3, that's what we said here, that to get power with our alpha beta is 2/3, and then sum that up and we get the 2.3 kilowatt hours. I hope this helped. That's it.